What if the moon merely rotated? We here on Earth would be able to look up and see all sides of the moon, right? Of course, Earth spins too, but to simplify our discussions, let's hold it still for now. Also, let's add a yellow line so to make the rotation of the moon more apparent. Note that as the moon rotates, the line goes from vertical to horizontal to vertical to horizontal and so forth. That means it's rotating. What if the moon didn't rotate and it only revolved around us, like this? We'd still be able to see all sides of the moon, right? What if the moon both rotated and revolved? How about like this? Look carefully, and you'll see that, yes, we still get to have a 360-degree view of the moon. No hidden sides. But what if the moon rotated just as fast as it revolved? Like this. Ooh, check this out. The moon is rotating, right? Look at the line, if you don't believe me. Vertical, horizontal, right? But it's rotating at a rate that matches the revolution. Just so that only one side of the moon ever faces Earth. And that's exactly the situation we find ourselves in today. The only side we ever see we call the near side. The side we don't ever see we call the far side. Actually, the first time we ever saw the far side was from photographs sent by a Russian lunar spacecraft in 1959. But no human ever saw the far side directly until the Apollo 8 mission in 1968. But why don't we, here on Earth, ever see the far side? Why does the moon spin exactly as fast as it revolves? Good question. And I mean, very good question. We could spend weeks studying this one question. But I'll just give you the quick explanation. For starters, let me tell you, it's no coincidence. Earth's gravity gets weaker with increasing distance, right? Yeah, but over the distance of a few meters or even kilometers, this difference is not that much. The Earth's pull of gravity on your head is, for all intents and purposes, the same as it is on your feet. The moon, however, is thousands of kilometers wide, so the near side of the moon experiences a significantly stronger gravitational field from Earth than does the far side. What this means is that the moon's center of gravity relative to Earth is not the same as its center of mass. Center of gravity? Huh? The moon's center of gravity is the point upon which all of Earth's gravity appears to act. You could scrunch the moon to the single point and, gravitationally speaking, there'd be no difference. If Earth's gravity acted uniformly across the moon, the center of gravity would be the same as the moon's center of mass, which is the average point of the mass of all the atoms within the moon. Yeah? But because Earth's gravity is stronger on the near side of the moon's center of gravity is shifted toward the Earth, like this. Now, the moon's center of gravity can be considered to be the point upon which the Earth tugs. If the moon rotated a bit faster or slower, the center of gravity would be lifted away from the Earth. And you know what happens to things lifted away from the Earth? That's right, they're pulled back down. The Earth would apply what we call a torque, which would align the moon right back to a position where the center of gravity is directly below the center of mass. Kind of like this. This is what prevents the moon from rotating any faster or slower than it does. The moon can only rotate so fast because Earth won't let it do otherwise. As a consequence, the moon rotates only once for every revolution, and only one side of the moon ever faces us. The differences in Earth's gravity between the near and far side of the moon has other effects as well. For example, it has the effect of stretching the moon into a somewhat oblong shape. This happens because the force of gravity isn't applied uniformly. Earth's uneven gravity acting on the moon causes an oblongish deformation. Remarkably, The moon has the same effect on Earth. This is most noticeable with the Earth's oceans, which are relatively easy to stretch. As the Earth rotates beneath this oblong shape, the sea level goes up and down. As we pass under each bulge, we experience high tide, twice a day because there are two bulges. The two low tides are when we pass under the narrow regions of this oblong distortion. This oblong distortion tends to hold the oceans still relative to the moon, so there's actually a bit of friction between the ocean floor and the water as the Earth rotates. This friction, combined with a small torque on us by the moon, is slowing our rate of spin. As I said earlier, back in the time of the dinosaurs, a day was about 19 hours long. In a billion years or so, a day will slow down to about 46 hours. At that point, only one face of the Earth will face the moon, much like only one face of the moon now faces the Earth. By the time this happens, the moon will be much farther away because of the conservation of angular momentum, which we haven't talked about. But like a fast-spinning ice skater, slowing down needs to throw her arms outward, the moon slowing down Earth can only do so by moving itself outward. Then the Earth and the moon will be completely locked in their dance around each other. Right now, the Earth is kind of shy and always turning away from the moon's constant gaze. But when Earth finally returns that constant gaze, when we're finally completely locked together, the moon will appear at a single location in our sky, day and night. People on opposite side of Earth won't ever get to see the moon, unless they go on vacation to the moon view side of our planet, where I'm sure real estate prices will be higher, along with the sea level. In a billion years from now, will we still be around? Oh, I got a question for you. Does the far side of the moon ever see the sun? Think about that. Oh, and can you ever see the Earth from the far side of the moon? Lastly, if you were right here and you looked straight up, what would you see? Would it ever stray from being directly above you? Ooh, good questions. Good science to you.